Hello, students. All right, I'm going to go over linear graphs and calculating the student t-test. So we start with the linear graph. So you're given a set of data, and you need to determine what kind of graph would represent the data best. For the section D for labs assignment, it's giving you time. So the first column is time, 2 minutes, 4 minutes, 6 minutes, 8 minutes, increments of 2 minutes. And then the second column shows you the heart rate. So for this data, the experiment could have been looking at what effect does exercise time have on heart rate. So the question is, what effect does exercising have on heart rate? Heart rate is how fast your heart is beating in a minute or in a given time frame. So for that type, for section D, that type of data lends itself to a linear graph. And a linear graph is going to show you a trend. Okay, we want to see, is there a trend to when you increase the amount of time, does that change the heart rate? Linear graph would give you that trend best. So the graph would have an X and Y axis. The x-axis, it goes on the horizontal line, that's the horizontal line. The y-axis is the vertical line. The x-axis represents the independent variable. The independent variable is what you manipulate, what you change to look for and record a result. In this case, your independent variable is the time. You're manipulating the time frame of the exercise. So at 2 minutes, you're exercising 2 minutes, recording the blood pressure. At 4 minutes, you're manipulating the time frame. You're looking at that time frame. You're looking at the dependent variable. How is the longer you exercise, how is that dependent variable changing, that heart rate? So the heart rate's the dependent variable. The time goes in the x-axis. The independent variable goes in the x-axis. The heart rate, what changes, the dependent variable, goes on the y-axis. So those are the components of the graph. Every graph has a title, a good title. So let's look at that data. We have exercise time in minutes, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and heart rate, beats per minute. It beats per minute. So at 0 minutes, at rest, you're not exercising right now, we could record the heart rate, and we would record 60 beats per minute. That's when you put your index finger, your middle finger against your carotid artery or your brachial artery, and you feel a pulse. So at this time, 0 without exercising, 0 minutes, the heart rate could be 60 beats per minute. Exercise 2 minutes, the heart rate goes up. So this table shows you that it went from 60 beats per minute to 70 beats per minute. At 4 minutes, now you're exercising 4 minutes, the heart rate's going up at 80. 6 minutes, 90, etc. How could we represent this data as a table now and look at it graphically? So what we do is we're going to graph here. So you're given that grid. The grid, it's just a box, so you can't edit the grid. You could hand draw it or you could create your own. What you could do to do that is you could go to Excel and you could copy and paste that information here. So here I've copied the table. I have 0 minutes, 60 the beats per minute, 60. 2 minutes, you have 70. 4 minutes, you have 80, etc. So I'm going to highlight here, and if you already know how to graph in Excel, beautiful. You don't have to look at this one. So I'm going to insert. And you know what? You could go through these different graphs or you could do recommended graphs. Now here, the best one, and it actually gives you a sample of how each of the data looks in the different types of graphs. So don't worry about it. It gives you a definition, a description. I know that a linear graph is what we're looking for. So a scatter chart is used to compare at least two sets of values or pairs data. Use it to show relationship between sets of values. A line chart, that's what I'm looking for, is used to display trends over time. I have time in my x-axis to 0 minutes, 2 minutes, 4 minutes. So this is the one I want to use. Or categories. So use it when there are many data points and the order is important. So I believe this fits under line chart. I'm going to put OK, and it generates the graph for me. I could edit this chart in Excel, but I'm not going to. I could make sure that I have a y-axis x-axis label and the chart title. So all I did was I just copied it, plotted it. You could plot by hand. At 2 minutes you put a dot at 60. At 0 minutes you put a dot at 60. At 2 you put at 70. At 4 you put 80. So you could do that by hand, of course. We'll go back to our PowerPoint, and so that's where I grab the graph. Is this graph done? Is this why I submit? The answer is no. What am I missing? So I need to make sure that I have all the components to my graph. I need to make sure that I have a title. I need to make sure that my x-axis is labeled. So this is my x-axis. And I have to make sure that it has the units. So my x-axis is what I manipulate, my manipulated variable, my independent variable. So my x-axis is labeled exercise time. And the units are in minutes. And then I need to make sure that the y-axis, the dependent variable, is labeled. I give myself enough room here. So we have heart rate. And then we also include the units, beats per minute. So now that's the title. Of course, don't title it title, give it a title. So that's the way you do exercise, I believe it's D from the lab submission. You graph it. You could do it by hand or you could do it computer generated. Make sure you have the y-axis labeled heart rate and the x-axis labeled exercise time in your units. Don't forget your units. And so here with this linear graph, you could see there's a trend. What direction is that line going? So the line that has an upward positive trend. What is this telling us? What is the conclusion that we could base off of this visual, the graphical visual? We could conclude that as exercise time increases, here we have 0, 5, 10. As exercise increases, heart rate increases. So we have this positive trend. The more you exercise, the higher heart rate. Graphs help us view the trend, view the data, and quickly make a conclusion, an analysis of the data a lot quicker than looking at the table or reading the text. Graphs are highly used to show that trend, to show the data in a very easy format to interpret. Now let's look at the T-table. So consider the following data. You're given the data for New York City marathon finishers. You're given the data for male and female. So for males right here on the first column, and then you're given it for females. You want to see, is there a significant difference in the finishing time of male runners versus female runners? So how would you go about this? You can take the average to determine if they are different. The average finishing time for males and the average finishing time for females. If you get a difference, how do you know that it's significant and it's not due to random chance? That's where the student t-test comes into play. You're comparing the means of two data sets. And with the student t-test, you could determine if this is a significant difference not due to random chance, or it's not significant, it's due to random chances. So let's take the average to find out what is the male's average finishing time. The male's average finishing time is 11,064.6 seconds. The female's average finishing time is 11,477.8 seconds. Now, how did we get the average? The average, also called the mean, it is the sum of each data point. That should have a little bar there. The sum of each data point for males over the sample size n. So the sum of each data point x over the sample size. How do we know our sample size? We count how many male data points do we have here. And so if you count, you have 15. So we go to the 15 mark. I mean, we're going to be here 15. Now, is this significant? 11,000 seconds versus 14,000 seconds. That's what we want to find out. All right, so before we calculate the t-test, we're going to do state our hypothesis. A hypothesis is a testable answer to your question. So there are two ways to state a hypothesis, your answer to your question. Now, what is the question? Let's review. The question is there a significant difference between the finishing time of male marathon runners' finishing time versus females' marathon runners' finishing time? The null hypothesis states that there is no difference. Okay, the null hypothesis in its shorthand H subscript 0 state that there is no significant difference between two groups of data, and for this data set would be written like this. There's a 95% certainty that there is no significant difference in finish time male versus female marathon runners. The alternative hypothesis would be the opposite of the null hypothesis. It states that there is a significant difference between two groups of data sets. So there is a significant difference between the finishing time of male versus female marathon runners. So let's start. These are the equations that you need to answer this question. Okay, the t-test equation is right here. That's what you're calculating. But before you could calculate the t-test, you need to know the variance, s squared here, and the standard deviation, s, because they're included here in the t-test. So where do we start? Let's start with the variance, but let's start with the sum of x squared. That's why we start there. Okay, so we start with the squaring each x point, and then we're going to add it. Okay. So we go here to our table. We have the males in the first column, and we're going to square each one of these. So squaring means you're multiplying that number by itself. So 9631 times 9631, 9,631 seconds. So 9,631 times 9,631 equals this large number. Okay? And we do that for each point. For each point. Okay, that's big numbers, that's correct. Well, anything we do to the data for males, we're going to do for the data of females, but I'm only going to walk you for the data for males. So once we square each point, we're going to add all of these. And that's this number here. And then we have a second table in your submission form that you're inserting these numbers. So the sum of x. The sum of x is just the sum of each data point for males. That's this number here, 165,969. N is your sample size. So that's 15. X with a little bar on top, that means it's the mean, the average of the data. And remember we did that. 11,064.6. Sum of x squared, that's what we just calculated. It's this large number here. So remember that this, you need to be careful with rewriting those digits because you miss one number and we're talking about big errors if you miss a significant number. So try your best not to miss a number. Again, you could use Excel to do the math for you at the number so you could reduce error. And then you're going to do the variance and the standard deviation. The standard deviation is the square root of the variance. So here's the setup for the variance. And again, is sample size 15. X, the sum of x squared, that's the big number that we did earlier, minus the sum of x, and then all of that squared. So you have that information here. Over, divide by the sample size times the sample size minus 1. Sample size times, that's multiplication here, 15, sample size minus 1, equals, and then you get your number. You do this for the male side and you do this for the female side of the data, okay? Once you fill up this table, then you could move on to do the T calculation because then you have all the numbers you need for the T calculation. Okay? So T calculation, this is the male, M stands for male, and that's the mean, okay, the average. So the male average minus the female average. Look at these here. These are called absolute values. So that means that whatever you get as an answer doing the average for males minus the average for females, you take away and ignore any signs, positive or negative signs. Okay, those are absolute values. You have to follow the order of operation. You always calculate what's inside brackets and bars and parentheses first, and then you go outside. So underneath here is the square root of the variance of males over the sample size plus the variance of females over the sample size, and then you take the square root of that. Um, and you calculate your t-calculation. So your t-cal is going to be a number less than 10. I know some of you are getting different numbers. It's less than 10, I believe. To determine what what you calculate means, we have to compare what you calculated, all that math that you did, which you're only asked to do it really just once. You have to compare it to the t-critical, okay? Now, in order to compare the t-critical is a number that you get from a table. You need the degrees of freedom. And the degrees of freedom is the sample size minus 1. Well, there are two samples here. There are male samples and the female sample size. So you have to count what's the sample size for males? It was 15. What is the sample size for females? It was also 15. So in this case, 15 minus 1 is 14. We get the same answer for males and females data set. The degrees of freedom is 14. Now, you won't always have the data where they match like that. So you always have to be careful that you do the degrees of freedom for each data set first. Which degree of freedom you use the smallest of the two. If you had a difference between the degrees of freedom of both data sets. In this case, it's 15 minus 1, 14. So we get that 14. We match it up to our t-table. And so at 14, it shows us that 2.14 is our t-critical number. So t-critical equals 2.14. Okay, that's the value we're comparing to our t-calculated. So how do we compare it? If t-calculated is greater than the critical t, then there is a significant difference. Okay, if t-calculator is less than or equal, this is what I'm looking at here, less than or equal to the critical t at our degrees of freedom of 14, there is no significant difference between two groups of data. So I have it here so you could fill in your t-calculated and let me know if it's less than or greater than. Accordingly, you will either accept your hypothesis, your null hypothesis, or reject your null hypothesis. Okay? So if t-calculated is greater than t-critical, then there is a significance. If there is a significance, you're accepting your alternative hypothesis and rejecting your null hypothesis. However, if the calculated t, what you calculate, is less than or equal to the critical t, then there is no significant difference. What does this mean regarding accepting or rejecting your hypothesis? If there is no significant difference, that's a null hypothesis. So you're accepting your null hypothesis and rejecting your alternative hypothesis. It's very critical that you understand how to interpret the data. T-calculation could be complicated because there's a lot of numbers generated and they're very big. Hopefully your rounding and your mistakes are small enough that you still don't alter the significance at the end, because we want to compare your t-calculate, t-critical. Try your best, but make sure that you understand how to interpret the data. And this is the key chart to interpret that data.